So let's take a look. Look at it. I'm just going to see about recording. I'm trying a new way of recording this stuff because of all the failed videos from earlier. So we're going to see if this works out. I'm going to try and figure out the net force acting on the charge at point S. Now, before I get on with this, it's incumbent upon us to recognize that the direction of our answer will require us to determine how we wish to address the direction of the force. And what I mean by that is, do we want to set an agreed upon zero for us to measure the direction and the relative angle of that net force? And if you're looking at me confused, like, do we want, say, this to be an agreed upon x direction, and therefore this to be an agreed upon y direction, and our answer will be made relative to those axes? Remember, you need to do that. This is not this class. This is any indication where you're dealing with vectors. That the direction of your two-dimensional vector must provide some kind of relative comparison. So there's no reason to use this one over others, but this doesn't seem like a terrible thing for us to do. Now, quite frankly, you all saying yes to that, you belie the fact that it would be so much easier. To use that as x and y. The forces are all along the x and y direction, naturally. And since this has got to be 30 degrees, we could do it this way, and then at the end, just turn it 30 degrees. Your math class has ruined you for this garbage. You know that, right? So, I'm not trying to be a jerk. I'm just trying to say, outside the box a bit. Come on, guys. Utilize some things that are here. So, I will do what you have asked, but I'm going to do the whole problem with my x and y lined up this way. Then at the end, you can tip it 30 degrees if you want to make it lined up with a horizontal. Okay? That means add or subtract 30. You'll figure it out. So, by doing it this way, I hope you see that there is if I put my little charge here, so Q is right there now, there is a force of repulsion between those two. That force goes this way, F. There is a force of attraction between those two. That's another force this way of the same magnitude. That okay? But there's a force this way too. And I'm thinking it's going to be less than that, but I'm going to put Fs for F small. Okay? Any question about that? Don't look at me like that, Ella. This is the way you do it. Are you looking at me? Oh, I can't tell anymore. With all the masks, and I'm not wearing my glasses because they fog up, I have no idea what Ella was looking at. But she just had this angry look. It's like anger. Is that it? Angry? Did you eat lunch today? We have a word for what happens when my daughters don't eat lunch. That they become hangry. And they are difficult to be around. Do you get hangry? Not if you eat. Exactly. I might get hangry. I just have a crappy lunch. It's really crappy. But it's lunch, you know. I'm going to say this, but understand that there's a problem with what I'm about to write. The net force is going to be 2F plus Fs, but it's really not an algebra addition. It is a vector addition. Because F is in the y direction, but fs is in the x direction. So although I will get to add them together eventually, I really probably should recognize that the net force in the y direction will be 2F, and the net force in the x direction is going to be little f. Right? That's just from the picture. We good with that? Make sure before I go on that you understand what I just wrote. Because eventually we have to get this, which is the net force, the total size of the force and its direction. These are just components of that force. We're making up the triangle part. So, I will need to consider this direction, or this distance. But luckily for me, this distance is just half of d. But I'm also going to need this distance, which is not half of d, but is probably related to something about a 30, 60, 90 triangle. But I know I got people who are going to ask me this later, which is just gonna not infuriate me, that's the wrong word, just going to make me a little crazy. So I am looking at a big triangle here, and I don't want to make a finer point of it. It's this side, and this side together. I'm going to use that triangle. We all see in that triangle? This side is D. I know I'm doing it very faintly, so it's not going to interrupt too much. And this side's R. So cosine of 30 degrees, that's this side, 30 degrees, is going to be R over D. We all good? So R is going to be the square root of 3 over 2 times D. We all good? You don't have to ask me later. We're all good. All right. So let me get rid of all of those things because it's just in my way, even though it's really light and it's just yellow. Yellow doesn't get enough credit. A little yellow. There we go. All right. All pretty. All ready to go. All right. So I think we've got everything we need. So let's look at F first. F is pretty easy. It's the force between, say, these two particles. So that's going to be q squared k over d halves squared. We're all happy about that? Which is going to be 4 q squared k over d squared. I can say yay and move on. Okay, yay and move on. Fs, that's the one that's from this distance, these guys right here. That's going to be q squared k over, in this case, d is root of 3 over 2d quantity squared. So that's 4 q squared k over 3d squared. Yay? Yay. Okay. I'm going to come over here now. Net force in the y direction. That's going to be 2 times that, so 8 q squared k over d squared. And net force in the x direction is going to be 4/3 q squared k over d squared. Tell me we're doing okay. Make sure, because it's going to get funky after this. Excellent. Okay? Everybody good? Everybody happy? We have this, right? These are our two vectors. And this is the y direction, and this is the x direction. Still good? We add vectors tip to tail, so and for the time being, I don't care. This is 4/3, and this part of the triangle is 8. So what is the net force? 8 squared plus 4/3 squared, all under the radical, times q squared k over d squared. That's going to be the size of the net force. I'm not doing it. It's on you. I don't think it's anything pretty either. So, stop it. You leave that crap outside. So, it's not, but I bet, we can get a 3 out of it in the denominator if we work hard enough at it. Because we're going to have common denominators anyways. And I can factor out that common denominator. I bet there's a 3 on the denominator of that. And the top's going to be some mess. Whatever 8 squared times 3 is plus 4 squared. 64 times 3. I don't want to do this in my head. You guys have freaking calculators. So what is 8 squared? I mean, David's bored. Come on, David. 8, what is it? I don't know. That's why I'm asking you. Don't tell me I think. If it's not right, one of these people in here is going to take me to task for it.
192.
This is the first part, David.
8 squared. Actually, it's 8 squared times 9
Yeah, it's 592.
plus 16.
That's what I got last night. That's what I just got now. 592.
592.
So I was right.
There it is. Now, I don't know if 592 has any reasonable factors. Doesn't matter. That's the size of the force. Pythagorean theorem. Of course, that's not enough. You want this angle too. But I'm thinking tangent has got us all locked up here, right? Tangent of theta is going to be 4/3 over 8. So I'm sure Joey can tell me what this angle is. Oh, really? So you're all nodding and everything, like, yeah, Miss Shelton, that's the way to go. I'm up here performing like some dancing monkey, and you're just, nodding at me. Come on. And it is. Yes, ma'am.
I got about 9.5 degrees or 9.462.
9 degrees. I'm good. 9. All right. Losers. So we have the magnitude. We have the angle. But remember, this angle is relative to the y direction that I chose here. If you want to tip it up, you're probably going to have to add or subtract 30 degrees there. I'll let you figure out which one of those you're doing. But I can tell you, not particularly challenging there, right? You can figure out what you have to do, because if I come back to this picture and tell you that it's 9 degrees from there, you might have to figure out what that means for tipping this whole thing upwards. Okay. The actual y direction is probably that way. I'm thinking it's like negative 21 degrees or 21 degrees to the side. This isn't drawn to scale, you know that. So you would actually subtract then 30 degrees from this 9 to get it if you wanted to make it relative to a vertical and a horizontal. But I feel as though we've talked this problem into the ground. Just beating on a dead horse now. Now, if you ask me for another practice, I'm going to say no. Okay? Grab your textbook and bang them out so that this becomes routine. I'm not going to take away the fact that we will still have geometric problems. Geometry is a part of everything we do this quarter and almost everything we're going to do fourth quarter. There's a lot of geometry in these questions, but never so much as you will have them in the next 2 months. Nail your geometry. Make it answer to you. I was going to say something else, but thought better of it. Make it answer to you. So I really want to maybe move forward a little bit. And I want to start by introducing you to what the real challenge is. Point charges seem great, but the truth is that's not how nature tends to work. So we have 2 places we're supposed to go, and one of them is to discuss the electric field, which is where we're supposed to be today. But the truth is we are still back on day 1, Coulomb's law. That's what we're still doing, Coulomb's law for point charges. And I had hoped to talk to you at least in a rudimentary way about what are called continuous charge distributions. And to introduce this topic, I want you to realize that when you charge something up, like a piece of plastic, strip away charges from it, and you charge it up, it can have some net charge distributed throughout the object. It's going to behave different than a point charge. Consider if I have a rectangle in space where the whole thing is charge Q, which means that I've taken a certain amount of charge and spread it out over the whole thing. How would a point charge placed here behave next to this charged bar? I can't treat it like a point charge. Now, I've placed it in the middle, so I get a little bit of symmetry, but you understand that this part of the bar is going to cause a force related to A, how far away it is, but also the fact that it's going to be in that direction. While this part of the bar is going to push straight down on it. And a part of the bar here in the middle, I don't know, this way? But you do understand that there's going to be a net force on that particle. A combination of all of these little pieces. We have to somehow find a way to add up all of the contributions of every piece of this bar to produce the net force on a point. This is a continuous charge distribution. And there's lots of ways in which continuous charge distribution problems can be presented. The finite bar is one of them. The infinite bar is another. A curved piece of charge. Now, to fully appreciate why we study this is to understand that antennas, it'll never come up in this class. It'll never come up for a long time. If you never pursue engineering, you'll never even know about it. But when we shape antennas to produce charges on particles, and we choose their shape based on the way they can apply the forces on those particles. We want antennas to maybe do better when some frequencies hit it than when others. So you want your Wi-Fi antenna to ignore the frequencies associated with Bluetooth, but amplify frequencies associated with Wi-Fi, so that they do a good job of connecting just to the Wi-Fi and not getting interference from Bluetooth. Because I'm confident some of you in your home at some point or another have probably streamed music while listening to Bluetooth headphones. Well, how does the device do that? How does it receive the signal from the Wi-Fi and then pass that signal to the Bluetooth antenna and send it to your ears without the Wi-Fi signal and the Bluetooth signal somehow interacting badly. Not to mention, Wi-Fi doesn't send music to your phone, it sends packets of network traffic to your phone that it must parse out and figure out which part of that packet is the music. And then create a waveform that it will digitally send over Bluetooth to your headphones, and your headphones will convert that digital information into analog sound. It's magic, right? As far as you're concerned, aliens made it. But a person sitting in one of these chairs actually made it. They just sat here a couple of years before you. I like them folding phones, though. Those look cool. I'm desperate for my own folding phone. And I don't mean like a flip phone. I mean one of those ones where it like magically has a massive screen and you can fold it. I'm waiting for one I can just fold away like small and just put in my pocket and open it up as big as my iPad. So, you know, it's coming someday. You guys need to make me some cooler crap, all right? I want to just unroll it and it's like right there and then roll it back up and it's just a tube. I get busy. I want cool crap, all right? I want the future now. I don't, and you know, I want to just put like a little box here and an entire screen appears on my table here, okay? I want things. And I need you guys to go make these things. So, no, I don't want new. I like my, I want the newest one. I want the one that's going to be coming out in 20 years. But I want it tomorrow. I'll wait till September, okay? So ultimately, continuous charge distributions require that we do something that you have never done before. And I'm going to be very clear about this. You've never done this before. It's not even taught in calculus. And you have to understand that those of you who are in calculus or have had at least AB to this point, you heard shades of what you're going to have to do in there, right? That I'm going to have to break this up into small pieces and talk about how each individual piece contributes to this force, and then add all those pieces together. That is calculus. And for those of you who are unfamiliar with what I'm discussing, you're at least familiar with the fact that the summation symbol suggests I can take something and break it up into small pieces and add up all those pieces. So one way to do that is actually to take this thing, this physical length, and choose an arbitrary number of pieces to break it up into. And assume that each one of those pieces, he put his hand up and said 2. Not even close. Not even close, buddy. So, yeah, I'm thinking like 10 pieces, you know, or 20, or 100. And recognize that even so, that's not going to give us the answer. It's going to give us part of the answer. It's going to give us an estimate of what the answer could be. So I could turn this from a single bar into 10 individual point charges, equally spaced, each one of them with 1/10 the total charge. And do the point charge problem we just did, but do it 10 times over. Recognizing there's some symmetry here. Right? I have some pieces that are going to cancel out, but also recognizing that with every different piece, it's a different distance away. It's going to be a lot of work. Now, that's not how we do it. It's not what I want you to be able to do. What we're going to do instead is we're going to learn how to find a way of expressing this as an infinite number of pieces. This is where we cross that line and go into calculus a bit. What I'm going to teach you is not calculus. I'm going to teach you how to form the integral. And then it'll be calculus's responsibility to teach you to execute the integral. So anybody who's had AB realizes that when you transition this to the integral symbol, because that's what this is. You guys who are new to calculus, the integral symbol is an S. It's purposefully an S because it means to sum. So they are both the same symbol and can be treated the exact same way. Both of them have limits where you start your sum and end your sum. The only difference is that the summation symbol gives you the iterative amount. N goes from 1 to 50 integrating by, or increasing by 1 or some step, where the integral gives you a starting point and an ending point. So they are the same. What happens in here, I want to make that up. I want you to be able to put what's in here. For the time being, you'll have to create the integral. You won't have to execute it, meaning you won't have to produce the result, because for the most part, most of you can't. In fact, I'll be honest, the finite bar, nearly an impossible integral for most of you. You'll probably not get to that in your calculus class. It's a tough integral. And I'm not leveling that as a challenge. Some of you will be able to do it. But you won't get to that material right away. The infinite bar allows for us to actually do the problem easier. The infinite bar has enough that cancels out that it works out easier. But the finite bar is hard. I'm just going to be clear, it's hard. I probably couldn't do it today without having researched my notes and gone up and looked up the integral on an integral table. It's a tough integral. You guys who are sharp, try it out. Now, yes, sir?
Does it have to do with like the mean distribution or like in stat? Or
No. Although there is a certain amount of statistical probability here, it's different than that. So no, that won't apply here enough. So what I'm going to do for you guys is I want to kind of step you through the set of steps that you'll have to employ in order to create an integral for a charge distribution. And every one of these steps is something you've already done. Because ultimately, all you really have to do is turn this huge bar into one point charge somewhere on the bar. And create Coulomb's law using a single point charge on the bar. So I want to show you how we do that, okay? So to do that, there are a couple of things that we have to kind of go through to get there. And the first is we have to provide at least the semblance of reference. Like, I'm going to tell you that my particle is a distance z away from the bar. And I'm going to tell you it's at the midpoint. These are things that set the problem up. They would be given to you. Our problem is going to allow us to use z in our answer. Because I think all of you probably realize that the answer we get here is probably related to how far away from the bar we are. Doesn't that make sense? That the value of this force would probably be greater if I was closer to the bar, and would be smaller if I was far away from the bar. The next thing I think you all probably recognize is that I have to assign a certain amount of charge to my point charge here, so I'm going to call it Q. I am going to say that the bar is L long. And I am going to say that the bar has a total charge value of Q. That's the kind of stuff that would be given in the problem. Those are all of our givens. Which also means that, except for fundamental constants, our answer can only have this information in it. Okay? So, once you have all of those things, your first step is to identify a single piece of charge somewhere in the bar. And also identify whether you believe this problem can be reduced to a one-dimensional problem, a two-dimensional problem, or a three-dimensional problem. Now, some of this is easy, some of this is more complicated. Can our bar be considered one-dimensional? And to answer that question, you have to ask, does charge on this side of the bar really apply a different force than charge on this side of the bar? Technically, the way I've drawn it, some of the stuff on the other side looks to be a little further away than the stuff on the inside of the bar. You have to ask if that matters enough. Generally, in the beginning, I will alert you to whether you have to worry about that or not. In this case, the problem will generally say something like this, that the bar is very thin compared to its length. We look for phrases like that in the problem. That phrasing, that the bar is thin compared to its length, tells you I don't have to worry about that. It's a one-dimensional bar. Now, if they give us this width and say it is W wide, oof, that probably means it's a two-dimensional bar, and you will have to worry about that. Okay? Now,